Welcome back. Let's start with the very first topic, regression, more specifically linear regression and least squares. So there are a bunch of videos over the YouTube about this topic, but I will be to the point and precise, and as you know, I only teach you what you need to know, what we use in practice. Okay, first of all, linear regression. We estimate the relationship between a dependent variable and one or more independent variables using a model that is linear with respect to the unknown weight parameters. To illustrate this point, let's say this is an independent variable. If you remember from the previous video, independent variable doesn't depend on other variables. It is like time, independent. And dependent variable in this case depends on the independent variable x. So these blue dots are the data points, and if you look at this, it looks like a line. I mean, you can extend it, right? It looks like a line. So I need to fit, let's say, a line to this video. And a line model looking like y hat equals to delta. Basically, this y hat depends on x. Two unknown parameters, w0 and w1. This is our model, and this model is linear with respect to w0 and w1, so that's why we are going to do linear regression. I would like to mention a few more things. I mentioned that here blue dots representing the data points. Let's say we have n data points. Basically, we are going to use these data points to train our model while finding w0 and w1. So you can consider this as a supervised machine learning, where we estimate the relationship between y and x using these training points. By the way, I started with the world's most simple model, line model. Later in the videos, we are going to look at more complicated models. As I explained in the previous video, since we can guess a data looking like this can be a line, this is a parametric model. And of course, there are data points that we may not guess a model. For those cases, we are going to deal with non-parametric linear regression using neural networks, polynomials, so on and so forth. We are extensively cover all of the topics, but we are going to start slow, as you are familiar with from my other videos on the other playlists. Let's start with line. Let's fully understand this simple case, then we are going to proceed further like a skyrocket. All right. Least squares. Basically, least squares is a technique that tries to minimize the actual data points with their estimates. And we basically capture this relationship using a cost function, v. This cost function depends on two unknown variables, w0 and w1, because our line or estimate how we stay close to all these points depends on w0 and w1x. For each data point, data I, for example, if you are looking at this is ith independent variable that corresponds to ith dependent variable. So we basically compare this with the actual y in a supervised learning fashion, take to the power of 2, and we would like to minimize this cost function. And once we minimize the cost function, we are going to guarantee that all these errors will be the minimal, so that we are going to get the perfect fit, line fit to this data that we have. So to wrap up, we would like to find unknown w0 and w1, initially unknown. After a while, when we solve this problem, it will be known. Find w0 and w1 that minimizes this cost function. And theoretically speaking, minimum occurs when change of v with respect to w0 and change of v with respect to v1 equals to 0. So when these partial derivatives equals to 0, then we can find the minimum, or more precise, the local minimum. We're gonna talk about those. All right, so now, first of all, I would like to represent this cost function without using this summation term. I would like to represent it using a vector matrix type of a relation. So I am writing the cost function again. This is the same cost function that you are going to see. Then I am expanding it, right? This is the from 1 to n. This is for the first data point. I just inserted x1 and y1. This is the second data point, x2 and y2. And all the way up to nth data point we have. I am assuming we have n data points. It can be 10, 100, depending on the data set that you are looking at. Now, from this step to this step, it is a little bit involved. I am not showing all the steps. You can try by yourself. But I can convince you, if you write this matrix multiplied by this vector and subtract y is the vector form of all these collection of data points. I just took down y1, y2, all the way up to yn. You are going to obtain this figure. So these two lines are perfectly equivalent to each other. This is an n by 2 matrix. I have all ones in the first row, because think about these like W0 multiplied by 1, W0 multiplied by 1, W0 multiplied by 1. So all these W0 points multiplied by 1. Second one, all these W1s multiplied by x1, x2, xn. So that's why the datas, x datas are here and the bias terms are on the top. This is the Euclidean norm to the power of 2, right? So basically, for a given vector, x, 2 is basically x transpose x, if you want to refresh your mind. Anyway, so these two lines are equivalent to each other. Then I am going to give this matrix a name, omega. This will be a vector v, and this will be a y. It is itself. And here are the dimensions. So basically, I wrote this cost function as 1 over 2n, all data points, Euclidean norm to the power of 2 of this representation. All right? And I will try to minimize this equivalent cost function to find the optimal W0 and W1 that fits to these points align in a least squares optimal fashion. All right, so more mathematically speaking, least squares deals with the problem of, in this case, I forgot to mention, right? I am going to call it from now on W. I would like to minimize this cost function with respect to W. And here is the cost function from the previous slide. And we mentioned that minimum occurs when these partial derivatives are 0. This is equivalent to gradient of v equals to 0. And gradient of v is defined as the, don't forget the transpose, dv over d0, this guy, and this guy here. Basically, if this gradient equals to 0, then we automatically satisfy these two conditions. This is kind of the vector representation. All right, so the natural question is how we can calculate gradient of v equals to 0. All right, first of all, gradient of v is partial derivative of v with respect to partial derivative of w. W is a vector right now. So I basically wrote the cost function in here. If you remember, this Euclidean norm to the power of 2 equals to this transpose multiplied by itself. So at this point, I would like to take the derivative. I need a formula. So I am going to the matrix cookbook. I shared the link with you in the previous video on this playlist, and I found this formula. And believe me, I don't get paid from Matrix Cookbook or anyone else. I am just doing this lecture series for your education and research purposes. So if you have a vector B, matrix A, vector Z, and if you are taking partial derivative of this with respect to Z, you are going to get this. I am using this exact expression from Matrix Cookbook. So partial derivative of this is equals to that by using this formula. You can stop the video, focus, this will be clear. If not, leave a comment, but I am sure it will be very clear. All right, so partial derivative is this. I would like to cancel these twos with each other. So the end result we have, partial derivative of v is this guy. So now what I'm going to do is going to set this to 0. I need to do that because of this. When I set this to 0, I am just getting rid of this 1 over n. 0 equals to omega y minus omega transpose v. I am distributing omega. 0 equals to omega y, omega transpose y. So now to find a solution to v, again, don't forget, I am trying to find a solution to v, to optimal solution. So this matrix needs to be invertible. If invertible, I can just multiply all from left by omega transpose inverse. Then I am going to arrive to this analytical solution. I am going to call it analytical solution. Some people call it direct solution. Some people call it exact solution. All mean the same. I prefer to call it, like the measure of the optimization people, analytical solution. All right. You may ask when this matrix is invertible. So dimension of omega, first of all, is n by 2. Little mistake here. So this should be 2 by n. Apparently this is 2 by n. Then I am taking its transpose. Its transpose becomes n by 2 multiplied by 2 by 1. So the correct dimension is this. I apologize for this. Turning back to our question, when this matrix is invertible. So basically this is a 2 by n matrix. Omega is a 2 by n matrix. And if you are multiplying here 2 by n, and if n is larger than 2, then it will be a, basically, we call it fat matrix. You are multiplying it with its transpose. This is omega multiplied by omega transpose. In this case, this is non-singular. So one point to remember, your number of data points in this case needs to be greater than the number of parameters you have. Basically, omega includes omega 1, W includes W1 and W2. We have 2 parameters to estimate, to find optimal points. So data points needs to be larger than the dimension of W, and then you can invert it. All right, so let's jump to a Matlab example. So here is the X locations or independent variables that I choose, and Y, 6 of them. And I am plotting them here with basically red. Here is the omega that comes from certainly 2 by n. N is 6 in this example. And I am finding the optimal solution, least square solution, inverse of omega transpose multiplied by omega y. And then I am generating, I would like to see if this is a good fit. So I am generating xp from 0 to 6. I am calculating y hat. Remember, y hat is W0, W1, the W parameters that I am going to find by solving this analytical solution. Then I am inserting it here, or in vector form, W0, W1 transpose multiplied by 1x. Again, it is coming from this equation. And then I am recording the data, then plotting the data. You can stop the video and understand this code. You can code it yourself. The end result, this black line that you see here, is the fit. This is the least square solution to the basically line fit problem to a data. If you remember, our basically model is a line equation. W0, W1 are initially unknown. We formulate the least squares problem, which is essentially a minimization problem. Then we find optimal V0 and V1 that minimizes. So all these distances from these points to data points to the line is minimal. So this line optimally fits to this data. All right. So please subscribe to the channel, turn the notifications on. If you like it, give a like. All right. Take care. See you in the next video for more exciting videos.